Good afternoon. My name is Josh Ruggles, and I am a master's student here at the University of Kentucky. I work in the Ampere lab under the guidance of Dr. Jiangbiao. Today, I would like to present on our research on online health monitoring of utility-scale solar inverters. The solar inverter plays a critical role in the solar system. It is responsible for converting the DC electricity that is generated by the solar panels into AC electricity so that it can be consumed by loads that are connected to the utility grid. The expected lifetime of a solar system is 25 years. However, solar inverters have an expected lifetime of just 10 to 15 years. Also, it is seen that the higher the power rating of the solar system, the reduced expected lifetime of the solar inverter. Utility scale inverters see a reduced expected lifetime of just 5 to 10 years. A study by Sandia National Labs showed that 78% of all solar system faults and failures were caused by the inverter, as shown here. To improve the reliability and availability of the solar inverter, an early fault detection and lifetime prognosis algorithm is proposed so that semiconductor switching failures can be predicted and diagnosed. This will reduce the downtime cost and avoid unplanned failures and outages. The system design which is being investigated consists of a 250 kilowatt PV array, a boost converter with MPPT controller, an active NPC inverter with space vector pulse width modulation controller, and an LCL filter. The active NPC topology was selected over the typical NPC topology for its improved efficiency and its inherent fault-tolerant capabilities. The active NPC used in our modeling combines silicon IGBTs with silicon carbide MOSFETs for improved efficiency and improved reactive power control. The silicon carbide MOSFETs will switch at the carrier frequency, while the silicon IGBTs will switch at the line frequency. The initial thermal modeling for the active NPC inverter shows a fairly even distribution of total losses amongst all switching devices. This contributes to a more even thermal distribution across switching components, which improves the overall lifetime of each device. The efficiency of the active NPC inverter is also very high and has a weighted CEC efficiency of 99.27%. The inverter lifetime estimation and lifetime extension algorithm is based on a hysteresis control loop which calculates the inverter losses and the temperature swing of each switching device. Using this temperature swing, the number of switching cycles to failure for each switching device can be estimated. Finally, based on the estimated number of switching cycles to failure, the lifetime of the inverter can be extended by reducing the switching frequency. To conclude, the solar inverter reliability has been a bottleneck for the reliability of solar systems, especially for utility scale systems. This research is proposing a fault prognostic and diagnostic health monitoring algorithm to improve the reliability of solar inverters. Currently, a baseline model of the solar system with a two-stage solar inverter has been developed in PLECS simulation software. The proposed fault prognosis and diagnosis algorithms will be verified in both simulation and experiments in the future. Thank you.